So, good afternoon. My name is Jan Pitel. I am the chairman of this session, interesting session, machining processes. We know that machining processes are a very important part of production, manufacturing, because effective machining processes can ensure the good quality, the economy, and so on. At the beginning, we had 4 presentations, but one presentation was closed. So we have 3 presentations. We have 1 hour. So that means that we have approximately 15 minutes for one presentation and 5 minutes for discussion to use all time for session. First presentation is from Lviv Polytechnic National University from West Ukraine. The presentation is titled Finite Element Analysis of Thermal and Strain State during Titanium Alloys Machining, and probably it will be presented by Xianing. Do you present? Yes? Are you present?
Yeah.
Yeah, okay. So
yeah, can you hear me? Yeah.
Please, you can present.
Yeah, okay. No, good afternoon, Mr. Chairman and Mr. Jan Pichel. No, okay, first, thank you for your introduction, and I'm very glad to have this opportunity to attend this conference. Yeah. So let me introduce myself. My name is She Xianning. I'm a Chinese, but now I'm a PhD student at the Lviv Polytechnic National University. Today, the topic of my report is finite element analysis of thermal and dielectric model during titanium alloys machining. Yeah. Okay. The second slide, please. Okay, thank you. Okay, let's start. Now, it is well known the most important characteristics of titanium alloys are high specific strength and low density in combination with high heat resistance at the temperatures up to 500 degrees Celsius, as well as a corrosion resistance in various chemically active mediums. At the same time, the mechanical characteristics of titanium alloys compared to heat resistant steel are significantly less. In the diagram on the right, we can see a comparison of titanium alloys with the most common materials in mechanical engineering. Moreover, in almost all indicators, these titanium alloys are the most effective. However, this is an expensive material and very difficult to machine. Yeah, next slide, please. These properties lead to the widespread use of titanium-based alloys in various industry as structural materials. Thus, titanium alloys are the main material for products of modern aircraft construction, rocketry, biomedical industry, and military industrial complexes. Increased corrosion resistance leads to the use of titanium alloys in the chemical, energy, medical industry, and other areas. Okay, next slide, please. But the machinability of titanium alloys is very low. The complexity of titanium alloys machining is 3 to 4 times higher than for Euro carbon steels, and 5 to 7 times higher than for aluminum alloys. When mechanically processing preparations for titanium alloys, it is recommended to use small cutting speed in small feeds with an intensive supply of lubricating and cold liquid. Now, this slide This slide shows the most important reason for the low machinability of titanium alloys, such as low speed machining, intensive operation, high specific tool wear rate, greater induced residual stresses, and given their description later. Yeah. Okay, next slide, please. Yeah. Now, as we all know, when the structure and the parameters of the machining process are planned, it is necessary to take into account the provision of wear resistance, residual stresses, deformations, fatigue stress, but not only the dimensional accuracy and roughness of the surface layer. This is because conditions of large cyclic force are thermodynamic laws during the product operation. Implementation of such technology should be carried out on the basis of function-oriented technology, which process is based on studying the workpiece, stress strain, and thermal state. This research and report addresses such problems. Next slide, please. Look, there are two main methods to study cutting dynamics. One, analysis of the cutting pattern. The two, real logical simulation of the stress, strain, and thermal state of the workpiece during machining. Moreover, the simulation type of research is carried out not only to establish the occurrence of the thermal-reticle foundations of the forming the surfaces to be machined, but mainly for the effective study of the dynamic stress strain state of the workpiece in different chip formation zones. Now, use the simulation data for the next step in optimization models. About this, what I want to say, the purpose is these structure parameter models can be used to effectively implement function-oriented technical process. Next slide, please. Yeah, look at the picture. The overall pattern of the stress strain state of the titanium alloy workpiece differs significantly from that of conventional materials such as steel or aluminum. Chips formed during cutting of titanium alloy have a sawtooth shape due to the high plasticity and toughness of the material. It's not just sawtooth shape. Yeah. Next, please. Look, in this slide, you can see the real picture of sawtooth chip formation captured with a high-speed camera. High plastic properties of titanium alloys during their machining contribute to micro and macro cracks in front of the tool blade. So here, you can see the deformation zone of the materials layer in dips and the formation of the residual stress zone. The results of such an experiment confirm the results of the simulation. Yeah. Next, please. Okay. This slide shows one of the results of a simulation of a titanium alloy cutting process in deformed software. In addition to the force parameter, we can obtain stress, strain, terminal field wear of cutting edge, loading, etc. A comprehensive analysis of all these parameters makes it possible to explain the cutting pattern and highlight those parameters. This most effective the machinability of titanium alloys. Yeah.
Sorry, is it possible to show the video for these slides, previous slides and these slides? Is it possible? Because this is unfortunately, because these slides implement to show what will be here the chip.
So please, can you show the ACE slide? Is possible? Last, yeah. No, the ACE. Yeah, ACE. Yeah.
It's impossible to show this.
It's a video or just picture? In fact, it's a video. Oh, okay. Okay, thank you. Understand. Okay, no, died next, yeah.
So you can continue.
Yeah, continue. Let's continue, yeah.
Next and next. And next.
Yeah, okay.
Previous, yes.
Yeah, okay, thank you. No, look, in this diagram shows the mechanism of a diabatic shear zone currency. Stage 1, yeah, just stage 1. The transverse cutting force of the maximum value. At the same time, the longitudinal cutting force has a minimum. The chip forming step occurs with the prevailing process of compression. The chip formation zone with the chip rods, conversely over the outer surface. And stage 2, opposite phenomenon occurs. Transverse cutting force takes the minimum value, and longitudinal cutting force maximum. This step corresponds to the complete prevalence of the shear mechanism with characteristics chip conversely over the outer surface. And the stage 3, the step of dominant compression of the chip formation zone is repeated. Yeah. Next, please. The following most important research results can be highlighted. Yeah, the cutting tips strongly affects the cutting force and chip ratio, chip thickness ratio. And for example, varying the cutting tips from 1.0 millimeter to 2.5 millimeter increases the cutting force by about 2 times, and increases the thickness ratio by about 1.6 times. A special change in these parameters occurs if the cutting tips increases beyond 2 millimeter. However, changing the cutting tips doesn't significantly affect the effective stress and cutting temperature. No, in fact, the results show from 1.5 millimeter to 3.5 millimeter, increasing tips by 7 times, but results in changing the parameters by 5 to 7% only. Oh, thank you. Yeah. look, the chip is sawtooth shape.
You can see a deformation zone here. Here. Let it be. Next. Let it be next video. This is a result for
Live.
It's on deform software.
deform software. Simulation. Yes, it is a result of simulation. Thank you, thank you. Now let it be.
Okay, can you continue?
Yeah, thank you. And 12, yeah. Next, yeah, 12, yeah, okay. The cutting speed has the greatest effect on the frequency of changing in the cutting load and chip signals ratio. For example, the cutting speed from 50 to 200 meters per second increases the rate of cutting force by about 8 times. This may be the cause of the high frequency toe oscillation. However, the cutting force decreases significantly as the cutting speed increases. For example, a four-fold change in speed, which is 50 to 200 meters per minute, results in a reduction in cutting force on the 25%. Which is 3.2 kilonewton to 2.4 kilonewton. Effective stress and cutting temperature doesn't vary much. Only only 7 to 10%. Yeah.
It is not so important. Please continue because you have a last minute.
Yeah, okay, thank you. Next, please. The geometry of the true cutting edge has a significant effect on the cutting load, chip thickness ratio, and processing temperature. For example, changing the rank angle from 10 degree to minus 5 degree increases the average cutting force by about 80%. It increases the chip thickness ratio by 27% and increases the temperature by 22%. In addition, increasing the rank angle results in a large variation in the frequency of cutting force, especially for toe with a negative rank angle. Yeah. Next, please. Okay, conclusion. The machine ability of the titanium alloys depends on the cutting parameters. The main causes of low workability are high cutting temperature, sawtooth type of chip. Yeah, and the second part has been expanded. Also, as we can see, simulation methods make it possible to study the details of the picture cutting and from the main ways to solve these problems with high machining property and low tool wear. Yeah, that's all. Next.
I'd like to set a little explanation for this, because I am co-author for this research, and the titanium alloys are very perspective and very interesting materials for operation, but for machining, this is a very, very difficult material. There are a lot of different scientific work for this, for explain the processes, but now we can't to finally understand why we receive the sawtooth chip, because there are I know 3 different theory, and everybody said that is more exactly results obtained. We make just finished the research in during the study in deformed system. Now we began the experimental work in study for these processes, and hope with collaboration with China University. You saw that there are very interesting results for using high-speed camera we use from China University, and we hope that result will be interesting, more interesting in future. Thank you.
Thank you for explanation, for nice explanation. My question was similar, but I have one question. This is a result. The presented results are from simulation, yeah?
Yeah. There are just only in simulation, but these results is same as results which appear with another researchers in this field. The adequacy of this result is too good. I think good, okay. Because the difference about 5, 6, 7%, not more. Really, system deform is very difficult system, and depend on different things. Some as for fracture, for example, fracture coefficient, and put in models. I work with this system more than 15 years, and I know they're all problems for this system, and I hope that in this stage we have a result to objective to adequacy. And for this experiment work, I think we make some changes for this. But
okay, thank you very much for explanation and presentation. Thank you. Okay.
Thank you.
So we will continue with another presentation. It will be presentation from Molutsk, I think. No, I don't see from I don't see the authors. This is a presentation on topic calculation of performance and relative consumption of diamond grains during high-speed diamond sharpening of superhand materials. It will be presentation as a part of dissertation research, and it will be presented by Dmitry Romashov. Is okay? Is okay? We have presenter. This is the last presentation. Yeah? Yeah, I see. Yeah, I see. Yeah, it's post presentation. Okay, so it will be presented by Alexander Grabchenko. It is a presentation from I don't know, from Odessa National Polytechnic University. Yeah, okay, I see already.
Yep, yep.
Thank you.
Yep.
Please, you can present your results.
Okay. Ladies and gentlemen, dear participants of conference, dear colleagues. Firstly, I want to introduce myself, Alexander Grabchenko, professor of Odessa National Polytechnical University. So, improvement the quality of cutting tool monitoring by optimization feature of the state space. In the conditions of modern industry level Industry 4, there is a continuous increase in the pace of technological processes. Accordingly, the process by cutting, the processing modes, primarily the cutting and feed speeds, were significantly intensified. This led to an increase in the rate of change of cutting tool state. In this regard, there is a need to improve the efficiency and quality of tool state monitoring of modern machine tools. The main components of the cutting tool monitoring process are, first, continuous or periodic cutting tool monitoring. Next slide, please. Using sensor of direct, indirect, or combined tools. Assessment ensures the receipt of appropriate signal of patterns, digital image of cutting part, for example, various signal of cutting system, machine drives, etc. Second, the processing of their signals by one or another method of the formation of sets of diagnostic feature that display the cutting tool state. Training of monitoring system, building classifier of cutting tool state. It's based on the formation of diagnostic features sets. Fourth, the classes of cutting tool states recognized in the feature space using the constructing according classifiers. Five, the cutting tool residual life predict and determinate by of the optimal moments of its replacement. The speed of cutting tool monitoring depends on many factors, and first of all, of the diagnostic feature, quantity, and quality. The initial space of primary features, Y, has a dimension n. The cutting tool state in the space which belongs to one of classes omega 1, omega 2, omega n, characterized by vector Y. The results of reducing its dimension, one of the methods of quality analysis is the formation of a vector of secondary features Y1 of n dimension. Next, please, slide. The aim of research is to develop an approach to improving the quality of cutting tool state monitoring based on the optimization of feature space of these states. As optimal criterion, consider the objective function which depends on the train time of the monitoring system and the quality of tool state recognition are used. The choice of the optimal method to using the dimension of the feature space may with the using the indirect method of mirror monitoring. Next, please. Research methodology. For checking, next slide, please. For checking the indirect control results credibility, the system of direct control which equipped with the special technical vision system was used. But in manufacturing conditions, widely use the method of indirect control. Consider the method of cutting tool state indirect control. Its main position are set in our publication 10. And the scheme for formation signal patterns of the cutting process when machining parts with mill using shown in figure 1. Please, next slide, figure 1. So, general structure of the indirect cutting tool monitoring methods is present on this slide. Next, please. Next slide, please. As a result of the experiments, a set of signal pattern of the cutting process with new and worn face milling cutters was used. This set used to form the optimal feature space of cutting tool states. The criteria for optimizing the feature space are: first, the speed of monitoring T, which directly relates to the number of diagnostic features used to recognize the cutting tool states. Second, monitoring quality Q, which is characterized by a probability of correct recognition P or probability of recognition error E. The block diagram of the algorithm for the formation of the optimal cutting tool states feature space is shown in figure second. Please, next slide. Figure second. Next slide, please. Figure second. Thank you very much. It includes two sequentially implements modules, blocks A and C. In the diagram, they indicate by dashed rectangles. The model for the formation of the space of primary features of cutting tool states A, the model for formation of the space of secondary feature of cutting tool state C. Input source date if the general case are allotted classes of cutting tool states, omega 1 to omega n, of dimension m to recognition. Sets of primary features, Y1 to YF, of dimension n, formed by processing signal from sensor or indirect cutting path control. That was presented in figure 1. Each vector arrives to input of cutting tool state classifier, which is constructed using the maximum likelihood method. Next, classes recognition is performed with the assessment of quality criteria Q and comparing them with the predetermined threshold value. When a position result is achieved Q more than Qn, further analysis terminated, the optimal feature space is considered formed. If the result is not achieved, no solution, this is transferred to the model C for the formation on secondary features. Next, please, slide. Here the features are the results of its wavelet transform, model D. The corresponding software package implements in the Python programming language. Let's go to proceed to consider the main results. Next slide, please. A training sample of the second order response of the indirect diagnostic problem used. A fragment sample of the second order response of the indirect diagnostic process used. A fragment of the training sample presented in the table 1. Table 1 is tab 1. The research results presented also in figure 3. The model A implementation of the process formation of the optimal feature space uses the initial vector Y in the amount of 10 primary features allowed us to obtain the results in two graphs. This is the graph of the classification error depends from the number of features, and a graph of the corresponding classifier time of the number of features. Please, next slide, it is possible. The result of the analysis shows in figure 3. This is a fragment of training sample for response is a features of first level. Next slide, please. The result of their analysis shown in figure 3. Figure 3, please. The recognition quality criteria were set. T equals 0.12 seconds, E equals 0.18. Figure 3, please. So, There is, we can see the results of the analysis of the cutting tool state recognition quality using primary features A and model A implementation of optimal cutting tool space forming process. As we can see, a solution was not obtained because the area of the intersection region S and M not existed. Next slide, please. In this situation, it is necessary to obtain the secondary features which we can obtain with the wavelet analyze using. Sorry. Next slide, please. The corresponding software package implements is a Python programming language. Here is a listing of one of the modules, model D, a training sample of wavelet coefficient of second order response of the indirect diagnostic problem was used. A fragment of the training sample presented in the table 2. Please, table 2. The implementation on model C of the process of forming the optimal feature space when using a vector Y1 is the amount of 9 secondary features allowed us to obtain the result in the form of 2 function graphs. Please, figure 4. Next slide, please. Thank you. The analyzed result of quality of recognition of the cutting tool states is the secondary feature. As we can see on this picture, the result is obtained because the area of the region C and M is intersection. So solution exists. Next slide, please. I see the time is absent, so please, conclusion. Hasbro developed an approach to improving the quality of cutting tool monitoring based on the optimization of feature space of various states. Two parameters used as optimization criteria, time and recognition quality. The approach demonstrates for option of indirect monitoring of the phase movement states based on the registration of processing of signal of the active power of asynchronic electric drive of main motion of machine. The method of maximum likelihood used as a method for constructing a classifier of cutting tool states. An algorithm has been developed and the corresponding software in the Python programming language has been created to optimize the feature space of phase movement state with indirect control using. The high quality of cutting tool states recognition is achieved by using secondary features obtained as a result of wavelet transfer of signals. Already preliminary research results, the use of 3 secondary features provide a classification of cutting tool state within 0.12 seconds with an error of not more than 0.18. The next result is the classification of cutting tool state in 0.15 seconds with a significantly smaller error of 0.1. In our first research, we are planning to reduce the classification error of cutting tool states to 0.5, 0.3. Thank you very much for your attention.
Thank you very much for the presentation. I have one question or one remark. We have a similar research. Our research is focused on toolsware.
Yes.
Yeah. My question is, your results are. It is possible to use your results for prediction of quality of tool.
Quality and cutting tool state prediction.
Yeah.
Yes, of course, of course.
Yeah, it's nice. Yeah.
Have a
Okay.
result in this direction, and I hope our future publication will demonstrate
Yeah. Okay.
this material.
Thank you very much. Any question, please? If no, thank you very much again.
Thank you.
And we will continue with the second presentation. It will be presentation by Dmitry Romashov. I don't know what is your university. Can you introduce himself? And please present your results of research. You can speak. You can speak.
Yes. Can you hear me?
Yes, I hear. Yeah.
Oh, yes. Hello, dear colleagues. First of all, I would like to congratulate you with the beginning of our great international conference. And my name is Dmitry Romashov. I am working at the National Technical University in Kharkov, Department of Integrated Technologies Engineering. And today I would like to tell you some of highlights of my dissertation, and a part of which is this presentation, the calculation of performance and relative consumption of diamond grains during high-speed diamond shuttering of superhard materials. Can we take the second slide, please? Here you can see the structural diagram of dissertation research in general. I mean, it consists of 5 different chapters. And here you can see the green one part. It's highlighted this calculation of performance and relative consumption. This structural diagram is the entire work in general. And I want to say that currently one of the most promising ways of improving the efficiency of grinding operations and expanding its technological capabilities is the increasing of cutting speeds. So what do we want? We want to apply the process of super high-speed grinding, and relatively recently, the technology of high-speed grinding has opened up the possibility for us to radically improve the efficiency, especially in surface quality. I mean, when you sharp the super hard material too. And processing of super hard materials is accompanied by low productivity and the high volumes of this relative consumption of diamond grains in diamond mill. The coefficient now of using these diamond grains in the process of sharpening super hard materials does not exceed around 5 or 10%. So also in this thesis, we want to study the possibility of using the high-speed regimes to increase this productivity of diamond grinding and diamond processing and sharpening of super hard material. Please, next one. The aim of the work is to increase the efficiency of high-speed diamond processing of super hard materials due to scientifically grounded determination of the characteristics of grinding wheel. To achieve this goal, the following tasks were solved. I just highlight a few ones. We're using a lot of 3D modeling analysis of influence the main parameters of grinding wheels, of processed materials, and the regimes of processing. Also, we're using a lot of particle information, and we have the correlation between 3D modeling and our experimental data. Also, one of the tasks is to investigate the process of high-speed grinding and to establish the influence of all the parameters of the wheel, processing modes, and on the efficiency of grinding process. Also, the main task of the work will be to develop some kind of product. So it will be like the expert system, which can be practically used for the high-speed grinding process with the wide range of parameters of two materials and coarse processing conditions. Please next one. Here you can see the concept of model experiment. This is the windows of the programs. It's SolidWorks, Abacus, and we're using SolidWorks, Abacus, LS-DYNA, and other third-wave Advantage, and so on. And also you can see these arrows, the green arrows, which are correlated between the experimental data and our 3D modeling research. Please. So, is it okay? Can you hear me? So we need to develop a general methodology of theoretical and experimental studies of the influences of quantitative and qualitative characteristics of the wheel and processed material, on the efficiency of their mutual microfraction during high-speed grinding regime. Here you can see, I want to highlight some interesting techniques. They were established during the internship of the author, in Texas A&M University, with experimental techniques on the TENSILE test. We can use it because we can see some structure, because it's using laser scanner and very, very fine microscope, so we can see the microstructure of our samples. Next one, please. Also, I want to highlight the experimental method of measuring NANO-HARDNESS of components of diamond wheels. Why is it so important? For example, diamond wheels have coatings of diamond grain, and if you need to measure the hardness of the coating, because it is very, very thin coating, if you will measure with the standard system, you can measure the hardness of not the coating, the thin film of the coating. You will measure probably the hardness and the specific properties of the coated material. For us, it's diamond. But this Fisher scope nanotester can measure everything inside this thin film coated diamond. This next one. This is sorry. This is shown the simulation. The simulation of the process of manufacturing of the wheels for high-speed diamond grinding or shunting. So you can see here the mathematical model, all the experiments. We also try to apply the experiments according to experiment planning theory, which allow us to obtain the mathematical dependencies for studied processes with a wide range of parameters. For example, we can vary different parameters, can be elastic modulus, coefficient of thermal expansion of the parts of the driving wheel of the tool. And of course, we can make, you can see here the resulting mathematical model after the significant number of modeling experiments. And using this mathematical model, we can calculate some statistics and, of course, obtain results, which can be correlated between experimental data. Please, next. Here I just can because we have not a lot of time. I can just I want to highlight this sum of results. This is showing the dependencies between CTE of metal inclusion and of course the temperature and pressure during the sintering of the diamond fluid. Please, next one. Also, the dissertation concludes the most important steps of life cycle of grinding wheels, and also it includes some calculation of the strengths, properties of grinding wheel in general, and also you can see here also the strength properties of the diamond, fixed diamond layer to the body of the grinding wheel. Because the high-speed grinding has a problem of destruction of the instrument during the processing. It is the safety problem, as well as the kinematics of the grinding machine. This is due to the huge speeds of rotation of the wheel during processing. Deformations also of working tool. There are occurring huge deformations of the working tool, and they cause the imbalance of the machine spindle and destruction of the wheel.
5 last minutes.
Yes. The next one. So you can see here the influence of rotation speed and temperature on the strength of the wheel structure. Of course, you see the graph. On the right, it's the experiment, the correlation between experiment data and our theoretical 3D model. Also, we are proposing some interesting ideas for improving the quality, improving the strength of the diamond tools, the diamond grinding wheels. And you can see here the calculation of the specific shape of the grinding wheels, and also with the drilled special holes across this fluid plane. So you see the plane where the diamond layer is glued to the body, and if you see the simulation here in the bottom, you see that the picture with these holes drilled with the specific angle. In general, the deformation and the stresses are going lower than with the first step. Also, we're calculating and simulating the high-speed grinding process. So it's the same as the sintering. We have mathematical model. We have the correlation between our experimental results, and we have the mathematical models which we can use when improving our expert system. Now this is the highlighted dependencies, stresses, the grinding area on the CTE coefficient of thermal expansions of the metal plate during high-speed diamond grinding. Also, dynamic modeling allows us to calculate the performance and relative consumption during high-speed diamond sharpening. You can see here the stresses and the broken diamond grains, and also broken processed materials, and graphs where we can see the dependence between the speed of processing and the relative consumption, and theoretical calculation of performance using high-speed diamond grinding. Please, next. I would like to show you the how can I say the most highlighted part of this work. It's the concept of this expert system of high-speed diamond grinding. So we have the place of our work in the industry 4.0 and also in using CLC technology. So we see the most important for industry, I mean, the most important for engineering steps of the life cycle of the different parts. So for us, it is diamond grinding used, and also the place of our expert system, which can be used also in Android applications, or well, it will be probably just a little bit longer, but it can be used. And the place, its place in this modern view of Industry 4.0. So we have a lot of modeling, engineering systems, cloud computing, and so on and so on. Please, next one. Here is the conclusion remarks. If we have some time, I would like to ask you not to read everything, but I would like to read the last one. So the proposed methodology can become the basis of the development of a scientifically
Last
based.
minute.
Yes. For choosing the optimal machining modes, combining greening wheels parameters when sharpening super hard materials tool with the framework of the fourth scientific and technological revolution. Thank you for your attention, and I'm glad to hear your questions.
Thank you for the presentation. It's a pity, but we not enough time, yes, because
yes, I was the last for today. Yes,
14. Yes, it's very nice. Because we have no time, so the questions are not possible. Thank you all presenters for very nice presentation, and I think that very interesting solves for further research and collaboration. Thank you very much.
Thank you.
Yeah, okay. Okay, but I have to find it. Yeah. Look at screen. Yeah. Oh, I didn't see it. I can't see it.
Vladimir Lebed.
Sorry.
Yes, I can. Good greeting to everybody. Our session is manufacturing technology. The first report will be the manufacture of cylindrical parts by drawing using oscilloscopic punch. Roman Arhat and co-authors Ruslan Puzir, Viktor Shetinin, and Mykola Moroz. Please, Roman, do your best. Do your best, I say.
Dear conference participants, a report is presented to your attention. The manufacture of the cylindrical parts by drawing using a telescopic punch. Please, slide number 2. Manufacturing of cylindrical parts from a flat round workpiece is based on the operation of cold sheet stamping drawing. This operation was widely used in production in the manufacture of a wide range of engineering products, aircraft, automotive, shipbuilding, instrument making, and other industries. It is also popular due to its high productivity and economic efficiency. It is characterized by the introduction of non-ACE technologies and obtained in parts that do not need finishing. However, the task of developing a rational technological process of drawing, which require the minimum labor input and the cost of manufacturing specified parts with the best quality, is still of particular relevance. Please, slide number 3. Aim increasing the competitiveness of enterprise products in the markets. Research tasks. Development and implementation of new schemes and methods of extraction. Intensifying the process as a whole and in each particular case of production to achieve optimal performance in terms of price quality. Next slide, number 4. Based on the literature analysis, a pressure-free stamping method using a telescopic punch was proposed. At the third stage of drawing, the punch deforms the workpiece along the outer diameter of the punch and reaching the bottom on the first step, the outer part stops. And further deformation is carried out by the in the main part until the finished product is obtained. In addition, with the reverse stroke, the outer part of the punch takes its inertial position with the help of springs compression moving along special guides. The punch design deserves special attention. Next slide, 5. Eternal punch 1 has a circular resource with dimensions B equals half D, A is equal to D plus 2 millimeter, where the diameter of the thrust ball fixing the external punch at the beginning of the operation stroke. When the external punch reaches the first stage of the die and presses the workpiece against it, it stops. Further lowering of the beam will cause the thrust ball to disengage from the internal punch, which is achieved by pressure of spring 4. After this, the shape is changed only by the internal punch, since the outer part will stop and slide along the surface of the internal punch and the key, which is installed and KY 9 on the internal punch. During the reverse stroke, the external punch returns to its original position and the action of the force of spring 7. Recess 8 has a radius of curvature equals half D in the upper part to release the thrust ball out of engagement and forms a step from below to fix the position of the external punch. The force of the pressure of the thrust ball to the internal punch is regulated using block 5 and screw 6. Next slide, 6. The pressure force of the thrust ball is calculated depending on the effort of the first stage of drawing. Slide number 7. The flange resistance to deformation and accordingly the highest tensile meridional stress during drawing without pressing the flange will depend on the following 7. Slide number 8. In this drawing method, the calculation of the spring force is of decisive importance since insertion present of the bolt holding the external punch will result in drawing only with the internal punch balls in the first stage, and in the second, excessive spring force will clamp both punches after the third stage and increases the pressing force, the external punch of the formed semi-finished product and can lead to reject in the form of a separation of the bottom. Therefore, it is proposed on the basis of research to refine formula in slide number 6. Slide number 9, 10, 11, and 12 to verify the operation of the designed punch experimental research was conducted. It aimed at measuring the drawing force of a proposed method and the operability of dependencies. Slide number 13. The presented method of drawing a cylindrical semi-finished product without fixing a ring contributes to the intensification of this shaping operation is based on a detailed analysis of against techniques for improving this process and taking into account most all technological parameters of shaping. The above graphical dependencies allow us to confirm the adequacy of calculated dependencies for the choice of punch, compression, springs, and the exempted assumption about the influence of the main process factors on the drawing force. The fundamental possibility of drawing by the proposed method is also confirmed. Technological calculation, this is the example above, makes it possible to move onto the design and calculation of die and power spring on the punch, which contribution to the manufacture of high-quality parts reduces labor cost and eliminates the use of a double-acting press. These measures will ultimately reduce the technological cost of the products. Thanks for your attention.
You're over? Then, gentlemen and ladies, any questions? No question. I don't hear the response. Okay. Then let's take another report. Thank you very much. Sit down, please.
Thank you very much.
The next report. Наступний доповідач. Study of the porosity based on structurally inhomogeneous material, aluminium titan. Олег Заболотный, Виктория Пастернак, Наталья Ильчук, Dagmara Nova, and Yuri Kulchuk. Please.
Good day. Slide 1. A report on the topic is presented to your attention. Okay.
Then show him, please. Там техника барахлит. Она и раньше барахлила.
Yes.
Yes. Begin, please.
Slide 1. Can I? Yes. A report on the topic is presented to your attention. Study of the porosity based on structurally incongruous materials OT. It's slide 2. Good. Introduction and major challenge. One of the areas of material science is the development of new materials using powdered metallurgy technology. That development objective needs are caused by the need to create fundamentally new structure and functional materials that have a sufficient level of mechanical strength at high loads, increased wear resistance, heat resistance, and low density. When manufacturing such materials with the necessary set of properties, it is necessary to control the parameters of the structure during the implementation of the technology at all its stages. This applies, first, to the operation of pouring into the mold, which is accompanied by the correct percentage of the original mixture. Therefore, progress in creating new materials requires a broad study and prediction of the structural characteristics of these materials, as well as the traditional methods of studying the structure of level intensity. Our urgent task is to improve, know, and to develop new methods for prediction the structurally and physical mechanical characteristics of materials. Next slide 3. Aim and research task. Aim. The purpose of the research is to investigate the physical and mechanical properties in the manufacturing of structure parts, to construct interpolation dependencies of porosity on the pressure and milling temperature, as well as on the distance to the walls of the hole. Research task 1. Develop a method for evolution. The main parameters of the full-scale powered filling process has been developed. 2. Receive the regular of structure formatation structurally inhomogeneous materials of OT samples. 3. Receive the dependencies of the structure influence on mechanical, physical, and mechanical properties, as well as the porosity from the distance to the mold wall. Please, next slide 4. Research methodology. The total mass of the initial components forms an aluminium, all which must be manufactured by using special technology progress of powered and lapidary metallurgy. Which 1 presents natural backfill shapes of powered of structurally inhomogeneous materials OT, where I all BT titanium. Please, next slide 6. Calculation. Yes, calculation of the initial components mixture OT. Calculation of the initial components mixture OT presented in slide 6. The mass of this mixture was calculated using the formula 1. The volume containing the components according to the theoretical single crystal density is using formula 2. The theoretical density of the initial mixture is using formula 3. The bulk density of the initial mixture found from the expression using the formula 4, after which we can find the volume according to the following formula 5. Please, next slide 7. Basic properties of OLT materials at different temperature. The main physical and mechanical properties of structurally inhomogeneous OLT materials are present in Table 2. Table 2 is basic properties of OLT materials at different temperature. Please, next slide 8. Results. General and sintered samples, which to its general compressed sample OT, and 3 its general view of the sintered samples OT. Please, slide 9. Depends of porosity on pressure and melting temperature for manufacturing structural parts, which for its depends of porosity on pressure and melting temperature, where A, its depends of porosity on pressure, and B, its depends of porosity on melting temperature. Please, slide 10. 10th slide, it's a microstructure of structurally inhomogeneous OLT materials samples. Which 5 is microstructure of samples of structurally inhomogeneous OLT materials at an increase of 800 microns, where A is before etching and B after etching. Please, slide 11. Interpolation dependence of the porosity based on theoretical and experimental data. It's feature 6. Interpolation dependence of porosity on the distance to the hot walls. Please, slide 12. Experimental and industrial justification of the result obtained. Feature 7. Its general view of the piston, where A in the compass software window and B photos of real cylindrical pistons. Slide 13. Conclusion presentation, slide 13. Among the main parameters of the full-scale powder filling progress has been developed. It was found out that the result obtained provides a visual representation of the particle size distribution, provided that the radius intervals in the fracturing are the same. It should be noted that the result obtaining all of to optimize the porosity of the result materials for specific functional properties and technology requirements of specific products. Experimental and industrial justification of the result obtained showed the proposed present ratio of the charge composition Warren provides a small mass of the initial components, high thermal conductivity, good anti-friction properties, which fully satisfies the technical condition of structural parts operation. Moreover, conduct the bulk of research without setting up expensive and time-consuming field expression. Please, next slide 14. This slide is references present reference. Please, slide 15. Acknowledgement presented in slide 15. The paper has been written with support of ASH project titled Directional Composition Thought Manufacturing Innovation, and a project titled A Policy Toolkit for the Promotion of Intercultural Components and Diversity Beliefs. Please, slide 16. Thank you for your attention.
Yes, I have done. Am I heard? Okay, then thank you very much. The third report will be minimizing surface roughness and radius error in laser cutting of EN10346 steel plate. Mustafa Kangal, Alper Yusuf, and others. Absolutely. Then Василий Маршили. Его запомнить.
Yes, yes, yes. Yes.
Oh,
Do you hear me?
here he is. So the next report will be solid lubricant used in small diameter drilling. Natalia Lipchenko, Vasily Larshin, and Irene Marchuk. It's better there to have no pictures of this woman. They are worth to be looked at. Then begin, please.
Yes. Put the first slide, please. Okay. Oh, come back. The first. Oh, okay. I am representing 3 co-authors. Natalia Lipchenko, Vasily Larshin, and Irina Marchuk. They affiliated with 3 known constitutions. Odessa National Academy of Food Technologies, Odessa National Polytechnic University, and Lutsk National Technical University. Next slide, please. Slide number 2. This is introduction and major challenges to our topic. It's possible to enlarge the vision, very small vision. My slide very small. Do you understand me? I don't read my slide. Very small. Okay. I have my slide here. Okay. Now slide number 2. This is introduction and major challenges. There are 2 main lubricants areas. The first, when lubricant is design material, machine working lubricant that ensures functioning machines and mechanism at the stage of the operations. These are lubricants decreasing friction and wear. Second area, additional means for improving the machinability of machine parts by cutting and grinding at the stage of their manufacturing. These are lubricants for metal cutting and grinding, or metal working lubricants. The functional requirements for the lubricants are due to these two directions. The first area, machine operating lubricant, reducing friction and wear of machine parts during the operation. This was first area. And the second area, metal working lubricant, distracting the material being machined. This was the second area. From the second direction, we have two kinds of lubricants. The first kind, solid lubricant. The second kind is liquid lubricant. And the third, gas lubricant. Our attention to solid lubricant. Please, slide number 3. Number 3. Okay, number 3. This is our aim and research tasks. The aim of research, as you can see, is studying the serpentinite containing a cell, this is solid lubricant, performance in cutting, small diameter drilling and surface grinding, including mixed lubricant with both SL and metal working fluid. Our research tasks are the following. The first task is friction coefficient comparative experimental studying on a special stand for contacting bodies in lubricating medium that contain different types of lubricant. The second task is developing measurement means including sensors, data acquisition computer device with appropriate software. The third task is experimental data acquisition and further comparative analysis of data during small diameter drilling with 3 repetitions of each experiment. And finally, the fourth task is the surface grinding experimental investigation in the combined, that is mixed, use of both the SL7 serpentinite contained and conventional metal working fluid, that is water-based 3-5% emulsion. Okay, number 4. Next slide, number 4. This is research methodology. There are 2 main directions of our methodology. The first direction is comparative tests of solid and liquid lubricants is performed on the stand, on the special stand. You can see on the left of the slide, This stand is equipped by measurement means. You can see one, this is spindle, 2, this is centering ball, 3, inner cup, 4, lubricant being tested, 5, external cup, 6, moving sample, 7, fixed sample, 8, ball thrust bearing, 9, beam with strain gauges. And second direction, experimental small diameter drilling with and surface grinding with mixed forced cooling. That is SL plus metal working fluid. Thank you. Slide number 5. Next, slide number 5. This is friction coefficient comparative studying. You can see friction ring scheme for calculation. The scheme has 2 radii. Radii number 1 and radii number 2. You can see also formula for the calculation the friction coefficient. You can see that friction coefficient is equal to the fraction whose denominator is T with index R and whose denominator is the product of two values, P and R. P is the axial load, which is given by the corresponding loads on the handle of the vertical feeding of the spindle, and R is the average radius of friction ring. You can see that if inner R number 1 and other radius with index 2 is equal 12 and 15 millimeter, then average R, that is average radius, is equal to 13.5 millimeter. Thank you. Next slide, number 6. Number 6. This is CNC coordinate boring machine, 24K4SF4. You can see three figures on the left, on the right, and in the center. On the left, you can see machine general view with CNC, flex, and C. On the right, you can see control program at the top and its embodiment at the bottom. And in the center of the slide, you can see drilling zone with drill bit of diameter is 2.85 millimeter. Thank you. Next slide, number 6. Number 6. No, number 7. Number 7. Okay. This is drilling conditions on the CNC machine mentioned above. The first idea, the subsequent tests are carried out on the coordinate boring machine equipped with flex and C system when drilling the blind holes. Drilling length is equal to 10 millimeter. In a workpiece of steel, 35 Germany analog with C35E hardness HB is equal to 190 and 210. Drilling parameters, drilling speed 2000 revolutions per minute, vertical feed 50 millimeters per minute. Drill bits with diameter of 2.85 millimeters are made of steel P18. Germany analog is mentioned, is indicated on the slide. The number of drilled holes for each SL formulation was equal to 30 pieces. And finally, each experiment was also repeated 3 times. That is, each solid lubricant formulation to be tested was successively tested with 3 different drills taken from one batch of the drills. It's important. With further averaging of the measured parameters over 90 drilled holes. Thank you. Next slide, number 8. Number 8. This is experimental results of the standard friction. You can see 2 figures on the left and on the right. On the left, this is dependence of friction coefficient on the so-called running in time in the interval of 50 minutes, figure with index A. And on the right, you can see dependence, the friction coefficients on the load applied. On the load applied. Oh, okay, it's well. Okay, it's well. On the very well. In addition of tonight, that is AIC, and the transition to the solid lubricant lead to a decrease in the friction coefficient. Thank you. Please, slide number 9. Next slide, number 9. 9. Okay. This is drilling parameters observed. Total torque designated by letter T with index sigma. You can see curve number 1. On the machine tool spindle, and total axial force designated by letter F with index sigma. Curve number 2. After the so-called sliding averaging, letters AG means the time interval of the drilling cycle. Sliding averaging has allowed to select a parameter by the calculation algorithm. I mean, 1 point from 100 previous and 100 subsequent signals readouts. As a result, the number of trend points is reduced to 200 times. At the bottom, you can see the formula. Measuring value designated by letter Y with index P is equal to the sum designated by the letter sigma. You can see two variables, B with index I and Y with index I. B with index I and Y with index P are the current signal level and the PS value of the signal average. Okay, next slide, number 10. 10. Okay. 10. This is mathematical models and levels of the torque signal. You can see two figures on the left and on the right. On the left, you can see dependencies of torque on the tau. Tau, this is time. And on the right, you can see the so-called construction of the signal models. Letters from A to E, A, B, C, D, E, shows different stages of the signal transformations. 1 on the figure is the total torque. 2 and 3 lines of the upper and lower thresholds. 4 useful torque. 5 useful torque trend. 6 the derivative of the total of useful torque as a synchronous signal. Thank you. The next slide, number 11. Number 11. Okay, this is changing the useful drilling parameters values designated by the letters T and F. T and F. On the left, on the right. On the left, you can see dependence of T on the number of experience. On the right, you can see dependence of force F on the number of experiments. Left part, 1 is dry drilling. 2, this is solid lubricant 4. 3, solid lubricant 2, and so on. Right part designated by letter B. Right part. 1 is dry drilling. 2, this is solid lubricant 2. 3, solid lubricant fund, and so on. Descriptions of the SL1, SL7 formulations are given on the next slide, number 12. Please, number 12. Oh, okay. These are 7 SL formulations. SL1, SL2, 3, 4, 5, 7. You can see that these are complex formulations. For example, SL1 contains oleic acid, 20%. For example, SL number 2 contains AIC from firm venture N, 2%, and stearin the rest. SL3 contains technical sulfur, 40%, and stearin the rest. SL4, you can see chromium oxide. SL5, you can see also technical sulfur, and besides molybdenum diselenate. Oh. And also polyisobutylene. SL6 contains acetanilide. And finally, SL7 contains serpentinite, 3%. Thank you. The next slide, number 13. These are our conclusions. There are 6 conclusions. The first, in the load range, the highest friction coefficient was obtained by testing the friction pair with the liquid lubricant, and the lowest friction coefficient with the cell on the steering base. Second, the use of NSLs mentioned in the presentation before allows significantly to increase the operation time of the drill bit until it breaks compared to the dry drilling and compared to the conventional drilling fluid. At ordinary drilling parameters and under otherwise equal conditions. That said, the most effective SLs which can be recommended to the further research and introduction into industry are the SLs containing molybdenum diselenate, sulfur, and serpentinite. Conclusions number 4. In the drilling small holes with a diameter of less than 5 millimeter, for example, 2.85 millimeter, the process performance is significantly improved when drilling using serpentinite containing SL compared to drilling using conventional metal working fluids. 5. The use of modern electron microscope with special software allowed confirming experimentally the diffusion penetration of SL components containing serpentinite into the surface layer of the cutting blade of the drill bit, which opens up the possibility for further research on the mechanism for reducing tool wear. And finally, in conclusion number 6, the effectiveness of the serpentinite containing SL for the surface grinding purposes of hardened steels in the combined use of the SL and conventional grinding fluid, that is metal working fluid, is shown. In this case, the SL improves the machinability of the working material in the grinding system, while the grinding fluid with work is being ground to prevent its temperature burns and deformation. Thank you. Next slide, number 14. Next slide, number 14. Oh, this is our acknowledgement. There are 2 sentences about what I would say. The first sentences. The work presented now was carried out in accordance with the state Ukraine budget theme of the Odessa National Polytechnic University from 1918 to 1921. The second sentence, and it's important, that this work is dedicated to the 95th birthday of Professor Alexander Vasilievich Yakimov, who was born March 16, 1925, who is the founder of the Scientific School on Grinding Technology and Automation of Grinding Operations, including the known intermittent grinding technology, as well as on the new solid lubricants development for cutting and grinding, etc. And finally, the last slide, number 15. Number 15, the last slide. The last slide. Oh, thank you for your attention, and I am ready to hear you.
Any questions, please, dear colleagues? No questions? Then, thank you very much. I think you're free now.
Okay.
So it was the last report from session 2. Is anybody